Hi, good afternoon all. Welcome to the weekly TCS seminar at Jagiellonian. Today our speaker is Martin Grohe from North Rhine-Westphalia Technical University of Aachen. So, well, our speaker's research interests covers a good chunk of theoretical computer science. This includes algorithm, complexity theory, graph theory, but also logic, database queries theory, and machine learning. So, among a number of results that I know, the closest one to my heart is the one on deciding first-order logic properties in lower dense classes of graphs. This result was mentioned last week because Sebastian Siebert was a speaker here. Martin also has a result of Daniel Marks that generalizes the structure theorem for graphs excluding fixed graph as a minor, as a topological minor. This extends the famous line of Robertson and Seymour on the graph minor structure theory. So, but today we're going to learn about something else, something different. So Weisfeiler-Leman Algorithm. This seems to be a heuristic on the graph isomorphism problem. We will see. Martin, thank you for joining us, and the floor is yours.
Okay. Hi, everybody. Thanks for the invitation. So yes, I'll speak about the Weisfeiler-Leman algorithm. Let me just share my screen. I hope you see the screen now. Okay, yes, let's assume you do. Okay, Weisfeiler-Leman algorithm is something I've been working on for a long time, maybe since 1996 or something. That's in some sense my first paper on Weisfeiler-Leman, I think Fox 96. Yeah, and I've picked it up on and off and done quite a bit with it in recent years. And the nice thing that only surfaced in recent years, that it has many connections to other areas, and these are connections that you wouldn't expect. So my talk is kind of a high-level overview. I'll explain the algorithm, at least the basic algorithm, which is very simple, and I'll explain some of its applications and some of the theoretical stuff we've been doing in recent years. And there's still many open questions and quite a few people looking into this. So I hope I can get you interested in this stuff as well. Unfortunately, it's not going to be graph structure theory or nowhere dense graph or anything deep, but still I like this stuff. Okay, let's see. Now I can. Okay, so the basic algorithm is also called color refinement, or the one-dimensional Weisfeiler-Leman algorithm, and that goes as follows. Basically, what we want to do is we want to compute a coloring of the vertices of a graph. And the idea should be if vertices are somehow different, or if we can detect a difference between vertices, we want to assign different colors to them. Okay, so ideally in the end, the color classes would just be the orbits of the automorphism group, but we will not be able to achieve this in this simple way. Okay, so how do we do it? It's an iterative algorithm. Initially, all vertices get the same color, and then we proceed in rounds or refinement steps. And in each step, we look at all nodes that still have the same color, and then we look at all colors and see if our two nodes have a different number of neighbors of some color. If they do, they get a different color now, okay? And we repeat this until the partition into color classes we get does no longer change. We're partitioning a set of n vertices. So after at most n-1 refinement steps, we're done. This will happen. The coloring stays stable, as we say. Okay, so that's the algorithm. And the algorithm has been reinvented independently several times in completely different context. And actually, the oldest reference that I know is from chemistry or chemical information systems, maybe, in this paper I'm citing here. Okay, but there have been various other occasions where this algorithm has been invented. And there are other names under which it is known. For example, in the graph isomorphism literature, it's often naive vertex refinement, they call it. Okay, and as I said, one-dimensional Weisfeiler-Leman is essentially also the same. I'm coming to that. So let's see an example. We have a graph here, and initially all vertices are blue. Okay, and now we are supposed to refine, and basically what we look at is if vertices have a different number of blue neighbors, so a different degree. And what we see in this graph, all vertices have degree 3 except for this one. Can you see my mouse pointer? Well, it's the one on the left side, the one that is red now. In the first round, this one vertex gets a new color and the other vertices all stay in the same color, and let's just keep them blue. Now the situation has changed a little bit. We have a couple of vertices which have degree 3, but now some have one red neighbor and 2 blue neighbors, and like this one here, and some have 3 blue neighbors. Okay, so they should get different colors. And indeed, the ones with the red neighbor are now orange, the other ones stay blue. Okay, what's the picture now? We have some vertices with 2 orange neighbors, some vertices with no orange neighbors at all, and some vertices with 1 orange neighbor. So we should see 3 new colors now. Indeed, 1 orange neighbor is green, 2 orange neighbors is yellow, and the rest is blue. Okay, so now let's see, we have, for example, here 1 green, 1 yellow, 1 blue, and here we have 1 yellow, 2 blue. What's this? That's also green, yellow, blue. I think that's what we have. So these 2 stay blue. This gets a darker green. Now, oh wait, something else happens. These 2 orange vertices have a green neighbor, whereas this orange vertex doesn't have a green neighbor, and this one doesn't either, so they should also get different colors. And these 2, I think, have become brown, and we have the split here. And now this yellow vertex looks different because it has a green neighbor. So in the next round, it gets a new color, and that's the stable coloring. Now, for example, these 2 yellow vertices have the same color pattern among their neighbors, 1 brown, 1 orange, 1 blue, and these 2 green also have the same, these 2 blue also, you can check that. Okay, so that's the stable coloring, and that's all the algorithm does. Okay, now this has first been proposed as a graph isomorphism heuristic. So how do we use it? Well, we apply to the disjoint union of our input graphs, the graphs where we want to find out if they are isomorphic. And the key observation we make is that the coloring is isomorphism invariant. Okay, it doesn't depend on the presentation of the graph, but just on the graph structure. Okay, so if the 2 graphs get a different coloring, that means if there's some color that's such that G and H have a different number of vertices of this color, then we know the graphs are not isomorphic, and we say that color refinement distinguishes them. Okay, now you may already see that this does not work as a complete isomorphism test, but at least if color refinement distinguishes 2 graphs, we know they are not isomorphic, so it can be useful as an incomplete isomorphism test anyway. Okay, it turns out color refinement distinguishes all non-isomorphic trees, so it can serve as an isomorphism algorithm for trees. On the other hand, there are very simple graphs that are not distinguished. Any two regular graphs that are not isomorphic will not be distinguished because on regular graphs, nothing happens basically. As you see in this example, we have two non-isomorphic, two regular graphs. What happens in color refinement? Well, all vertices have two blue neighbors, so nothing happens. Okay, and color refinement will just tell us both graphs have 6 blue vertices, which doesn't help us at all. Okay. Now let's talk about the running time. It turns out that color refinement is extremely efficient. That's why it's so useful in practice. Even if it's not a complete isomorphism test, it's used as a subroutine in almost all graph isomorphism tools. And to see what kind of running time we can achieve, let's just look at graphs with n vertices and m edges. Then it can be shown. Well, if we implement it in a naive way, we would probably need something like time n times m, would be my guess, if we're careful at least. But we can be more clever and achieve a running time of m times log n, or n plus m times log n. And the way we do this is something that you probably have all seen in a class on like basic theoretical computer science, minimizing finite automata. Hopgroth has devised an algorithm with a running time of n log n. And the idea is to not do all the refinement you can in every refinement round, but refine asynchronously. And then there's a strategy. If we split a color class, then we don't have to use all parts for further refinements. We can always omit the largest one. And that gives us the speed up that in the end leads to this log n. Okay, so that's an old algorithm. A while ago, we were wondering if you can do better, if you can do it in linear time. And well, we couldn't find a linear time algorithm. So we thought about if we can prove something. Probably not that it's not in linear time, because we don't know better than linear lower bounds for any problem in polynomial time, at least not for explicit nice problems. But what we could show is that for a large class of algorithms, certain partitioning algorithms that cover basically all known color refinement algorithms, this m log n is the best we can do. Okay, but it's still a very good running time, almost linear. There are no big constants involved here, so this works extremely well. And yeah, I'll show you how to use it in graph isomorphisms tests in a minute. Now, let me briefly speak about a few variants of this. On directed graphs, we would probably treat in edges and out edges separately. So count the in degree and the out degree out of all color classes in the refinement. So we can easily do this. On labeled graphs, we want to incorporate vertex labels into the initial coloring, and edge labels, basically, we consider differently labeled edges separately in the refinement step. So we ask how many red edges are there into the color class green. Okay, so that's easy. We have an interesting version for weighted graphs. Of course, we could treat edge weights just as colors, but we can do something else. We can say instead of degrees, we refine by the sum of the incoming edge weights. And we will see later that this can be very useful. So what we do in the refinement steps, we say two nodes V and W get different colors if there's some color C, such that, well, the two nodes do not have different degrees into this color class, but the sum of the weights of all edges from vertex V to a vertex of color C and vertex W to a vertex of color C. These two sums are different. Okay, and this alpha here is the weight of the edge VW. If there's no edge, we just say weight 0. So this, in a sense, does not lead to the finest possible coloring. Finest possible coloring we would get if we would just say edge weights are like edge labels and we do the labeled versions. But this is still useful. We're coming to this. Okay, and all these variants can also be implemented in time m log n. Okay, so originally this was devised as an isomorphism test. We have seen that it's incomplete, but we can still use it for isomorphism testing. So what we do is, or what basically all graph isomorphism tools do, they combine it with a backtracking search. And the way this goes, I can explain at this picture. So here we have a graph. We run color refinement, and basically our goal is to not do isomorphism, or at least not in my explanation, but to just achieve a coloring where all vertices have different colors. And if we do this on two graphs, we can easily compare them. So if we have two colored graphs and all vertices have different colors, it's very easy to check isomorphism, because we just have to check, is there an edge between red and blue, and is there an edge between blue and green, and so on. And then we see if the graphs are isomorphic. So here our goal is to somehow, in a canonical way, find such a discrete coloring. Well, we start with color refinement, doesn't work. We have two color classes with 3 vertices on this graph. And now we say, okay, let's split this. And we split it artificially. We just try the 3 vertices and see what happens if we assign artificially a new color to these vertices, like a purplish color. Okay, so here we try that vertex, there we try that vertex, in the 3rd branch it would be that one. Okay, now we have this graph and we run color refinement again. Now, since this vertex has now this purple neighbor, it also gets a new color, light blue. But still, the coloring is not discrete. We have 2 blue and 2 red vertices. So we repeat this procedure. We split the class. We say, okay, let's make this blue one green. And we have 2 choices, either the left or the right. Okay, so 2 branches here. So if this is green, then the leaf attached to the green vertex also gets a different color than the leaf attached to the blue vertices. So now we have a discrete coloring. And here as well. And we build the whole tree. And then at least we have a tree which is canonical, which is isomorphism invariant. And at the leaves, we have all these discretely labeled graphs. And then if we have another graph and we want to test isomorphism, we can compare the two. Okay, so that's the basic idea. Now, of course, the trees can get exponentially large. And to make this efficient, we use quite a few very clever pruning strategies I don't want to get into. But one of the main reasons this works well is that most of the time color refinement does almost all the work. I mean, the graphs usually are not so symmetric that you have few large color classes. So most of the time, color refinement does almost all of the work, and we don't even have to build a big tree. Okay, so that's graph isomorphism testing. Okay, the practical tools use this, and the idea is based on a paper and a tool called Naughty by Brendan McKay, and that was already from 1981. And most of what happened since then on the practical side is to refine these ideas, find good pruning rules and so on, efficient implementations and clever engineering and all that. Naughty is still a competitive tool. Of course, it has also been developed further since 1981. All right. Now I want to go a little bit into the theory of color refinement. And I think this is the part where it gets nice. We will see quite a few different characterizations of color refinement. And the first is in terms of graph homomorphisms. You know, a homomorphism from a graph F to a graph G is just a mapping from the vertex set of F to the vertex set of G that preserves edges, maps edges to edges, okay? And we're interested in the number of homomorphisms. That's this number here, hom of FG. And the result is that it's due to Dvorak that for all graphs, the following are equivalent. Color refinement does not distinguish the graphs. And for every tree, we have the same number of homomorphisms from this tree into the two graphs. Okay? So I'm not going to tell you how to prove this. It's not terribly difficult. I want to move on with another characterization. Actually, I'm not going to show you any proofs, but just give an overview on what is known. Anyway, so we want to look at another characterization, and that starts from a linear programming approach to graph isomorphism testing. So let's say we want to test if two graphs G and N are isomorphic, and we can assume that they have the same number of vertices, say N, because if they don't, they are not isomorphic. Okay, and then let's say the vertex sets are V and W, and the adjacency matrices of the two graphs are A and B. Okay, then the two graphs are isomorphic if and only if there's a permutation matrix satisfying this equality, X transpose times A times X is B. So that basically means permutation matrix means you have exactly one entry in every row and in every column, and the rest is zero. And they encode permutations in a way that multiplication just means transposing. So if AX means we transpose, I think, the columns according to X, and then X transpose times this thing means we also permute the rows. And we have to apply the same permutation to rows and columns, and then we want to end up with the other graph. Then they are isomorphic. Okay, so we can do that, and we can rewrite this because permutation matrices are orthogonal, so the inverse is just the transpose, and we can write this as AX equals XB, which is nicer because this is linear. Okay, so we can write this as a system of linear equations like this. So this here is basically the equation AX equals XB. I shouldn't touch my mouse. This here is saying that the row and column sums are all one, and then we say, okay, we want to look at integer solutions or non-negative integer solutions. So then this here, the row and column sum 1 implies that it's a permutation matrix. Okay, good. So we have this integer linear program, if you will, which is hard to solve, but we can look at the LP relaxation. So instead of looking for integer solutions, we can just look for rational solutions. Okay, so non-negative integer solution to these systems are isomorphisms. Non-negative rational solutions we call fractional isomorphisms for obvious reasons. Okay, and we can also view such fractional isomorphisms, going back to the matrix version, as doubly stochastic matrices. So row and column sums are 1, all entries are non-negative. Okay. And then there's a very nice theorem due to Tinhofer saying that color refinement does not distinguish two graphs if and only if there's a fractional isomorphism between the graphs. Okay. So now we have already two different characterizations which have no obvious connections either to color refinement or to each other. So one by homomorphism counting homomorphisms from trees, one by this system of linear equations. Okay, and let's move on a little bit with this. Now that we have this fractional isomorphism means AX is equal to XB, or isomorphism AX equal to XB. If we look at permutation matrices, we can say, okay, now let's say the graphs are maybe not isomorphic, but we want to find out how similar they are, or we want to solve isomorphism just using some optimization tool. So what we can do is we can just minimize this expression AX minus XB and then take some matrix norm of this, say the Frobenius norm of this matrix, and let X range over all permutation matrices. Now, minimizing over permutation matrices is something that is extremely hard, that you cannot do easily, or neither in theory nor in practice. But then we can look at this relaxation where we minimize over doubly stochastic matrices. And that turns out to be a convex minimization problem, okay? Because the doubly stochastic matrices form a convex set, and we can apply convex optimization techniques. So that's very nice. And then we can use standard algorithms. For example, one is the Frank-Wolf algorithm. And something we noted in this paper here is that color refinement essentially does the same thing as the Frank-Wolf algorithm. It's also, an iterative gradient descent algorithm, and the steps done by these algorithms are more or less the same than the steps of color refinement. Okay, and we can also use this to devise a new algorithm for color refinement that works in a power iteration style, like power iteration for computing eigenvectors of matrices. Okay, which in a way is quite efficient, at least if you have the numerical machinery for this. Okay, now let me digress a little bit from color refinement and look back at the equations. So we looked at non-negative integer solutions, which are isomorphisms, and we looked at non-negative rational solutions, fractional isomorphisms corresponding to color refinement, and tree homomorphisms. Now, what if we just look at rational solutions? Okay, let's do this. So what we have so far is that the system has a non-negative rational solution if and only if for every tree the number of homomorphisms of the tree into G and into H is the same, if and only if they are not distinguished by color refinement. If we drop the non-negativity, then we always almost get the same characterization, except that now we have to look at homomorphisms from paths instead of trees. Okay, that corresponds exactly to arbitrary rational solutions. Okay, so much for this. I want to talk about one application of color refinement that I really like, and that is to linear optimization. Basically, what we want to do is we want to use color refinement as a pre-processing tool for linear optimization. Okay, and the way we do this is as follows. Let's say we have a matrix. Okay, that will be the matrix of a linear program, and we view it as a weighted bipartite graph. Okay, and then we run basically color refinement on this bipartite graph. We just start from an initial coloring that already separates the two sides of the bipartite graph, okay? And that we call matrix color refinement. So let's see an example. We have this matrix here on the left, and I've drawn the graph on the right, and the edge weights are on the edges. I didn't put a 1 if the edge weight is 1, and weight 0 means no edge. Okay, so let's run color refinement. We start from a coloring that separates rows and columns. So rows are blue, columns are green, okay? Now we run color refinement, and color refinement on weighted graphs. That means we refine by the degree sums of the outgoing edges. So for example, R1 has 0.3 plus 2 plus 1 plus 0.7, weight 4 into green, okay? So the total weight of green numbers is 4. That's the same for R2 and so on. Now, if we look at the columns, they of course have blue neighbors. Now here we have 2, here we have 4, so that C2 should get a different color. The rest turns out to be 2. So everything stays, but C2 gets a new color. Okay, now something has changed because R1 and R3 have weight 2 into the red color, and R2 has weight 0. So they should get different colors. Okay, R2 gets a different color. Okay, and that turns out to be the stable coloring of this matrix. If you check, everything should be, I mean, all the degrees should match now. Okay, so that's how we do it. And we can still do it as efficiently as the basic color refinement. And now let's look at this linear programming thing. Let's say we have a linear program like this: minimize C times X subject to AX equals B, and the X are non-negative. Okay. What we do is we look at this matrix here. We take the A and then put B on one side, C there, and here just a symbol that is different from everything else. So this will get a new color right from the start. We compute the stable coloring of this matrix. Okay. And now we look at the number of color classes. And then what we do is we reduce our linear program to a new linear program whose matrix is just a K by L matrix instead of the original M by M. And if there are few color classes, this will be much smaller. Okay. And essentially what we do is we average over the color class. We take the averages of the entries in the color classes. Okay, so we get a new linear program, and then it turns out that we can translate feasible and optimal solutions easily by linear maps between the two spaces. Okay, so the new program has solutions in R to the L. The old one was in R to the N. So we have this projection matrix, which essentially encodes the stable coloring, maps between the two spaces, and it translates between feasible and optimal solutions. Okay, goes both ways. So if we're lucky, we apply this, we get a much smaller linear program. Then we solve the small one, okay? And then we can just pull the solution back. Now, of course, we're not always lucky, but in particular, in inference problems in AI, we often have linear programs that have many symmetries, okay? And for these, we will have few color classes, and the new matrices will be significantly smaller. So this really helps us and speeds up the solution. And so we ran some experiments. Basically what you see here, if you just solve the linear program, the original linear program, you get the blue line. If you apply our methods, and that's the total time for the method, you run color refinement and then solve the smaller one. You stay significantly below that. often by quite a bit, because here we have an exponential scale. And now the green stuff is the comparison with a symmetry reduction method, where instead of color refinement, we compute the orbits of the automorphism group and refine with that. So since it's expensive to compute the orbits, that's often slower, sometimes faster, but never faster than the color refinement thing. Okay, so much for that. Now, finally, we see Weisfeiler-Leman that I promised in the title. So what is Weisfeiler-Leman? Basically, it's a k-dimensional version of color refinement. So instead of coloring vertices, we color k-tuples of vertices. Goes as follows. Initially, we color all k-tuples according to the isomorphism type of the subgraph they induce. And then in each step, we do a refinement and we look from one k-tuple at all tuples that overlap with this tuple in all but one component. So that would be the neighbors in some graph of k-tuples, and we essentially run color refinement on this graph of k-tuples. Okay, that's Weisfeiler-Leman. So let's see an example. Here we have a very simple graph, but just to explain this stuff, cycle of length 8. Okay, what's the initial coloring? So we color pairs, and everything is symmetric here, which is not always the case, but happens to be the case here. So we have 3 isomorphism types of graphs. Basically, we have the 2 tuples where both components are equal. They get a dark green. We have an edge between the 2 entries of a tuple is light green, and we have no edge, that's gray. Okay, now we run refinement. And for example, okay, let's just see what happens. If we look at this pair, was gray before, but now the 2 endpoints have a common green neighbor. Whereas if you look at this pair here, this is not the case. That's why we have this new bluish color, which is now different from the old gray. So we get this, and that's the final coloring we get, basically encoding the distance of the vertices in this cycle. And turns out that these are even the orbits of the isomorphism group. So indeed, that's the stable coloring. Now, this example is special compared to the general case. All colors are symmetric, so they are undirected. The 2 components of the pairs, it doesn't matter where they are. And the color classes coincide with the orbits of the isomorphism group. In general, neither is the case, okay? But that should give you an idea of how this works. Okay, now, to implement this, of course, is much costlier. We need a lot of memory, basically n to the k, because we will have to store a coloring of n to the k many different tuples. Now, once we have that, to implement this, we need time n to the k plus 1 times log m. So if we want to do this in practice on larger graphs, we can probably only do it for k equals 2. But even for k equals 2, it's kind of a powerful method. Okay, so how does it relate to color refinement? Color refinement is essentially the one-dimensional version. Okay, 2 graphs are distinguished by one-dimensional Weisfeiler-Leman if and only if they are distinguished by color refinement. So all the results we had before about color refinements can also be phrased in terms of 1 WL. Something we have looked at quite a bit recently is how many iteration steps we need to reach the stable coloring. Okay, and it's easy to see we have a coloring of n to the k elements, so a sequence of refining partitions. That's basically what we have, and we can have at most size of the space -1 many such refinements of partitions. So that's the trivial upper bound on the number of rounds. but can we reach this? And it turns out for the one-dimensional version, we can reach it. Sandra Kiefer and Brandon McKay proved this. How about higher dimensional? Well, we can't. It turns out that for KWL, we need at most n to the k-1 rounds times log n, okay, which is significantly less than n to the k. Okay, so that's actually, it's something we proved recently, but it's a generalization of an earlier result by Lichter, Ponomarenko, and Schweitzer for k equals to 2. And that uses some quite nice algebra representation theory, essentially, to prove this. I don't know of a combinatorial proof of this result. We really need to go through some somewhat advanced algebra to get this. Okay, what about lower bounds? Well, we can prove that if we look at relational structures with k-array relations, then we can prove a lower bound of n to the omega of k, okay, which is not too far from the upper bound. For graphs, we know much less. The only thing that we have proved recently, so basically for a long time, the best known lower bound was just linear, so at least n rounds. We could improve this recently to n to the 1.5, okay? And yeah, the lower bound constructions are tricky constructions, basically using Weisfeiler-Leman type gadgets, if you have seen them, but then some nice compression arguments which go back to propositional proof complexity. All right, so much for this. We had these nice characterizations for the color refinement algorithm. It turns out they all generalize to Weisfeiler-Leman. So let's go over them. The first is homomorphism counting. So one-dimensional Weisfeiler-Leman was characterized by homomorphism counts from trees. If we replace tree by graph of tree with k, we get a characterization of the k-dimensional Weisfeiler-Leman algorithm. So this is very pretty. In particular, I mean, these things are not really hard to prove, but it's surprising that the characterizations are so nice and clean. We have another result which again requires some algebra to prove it, which also generalizes the path thing to path width k. So I still find this extremely surprising that things work out so nicely here, but that's how it is. And it goes on. Basically, if we look at our linear program and then the Sherali-Adams hierarchy above that, that gives us a characterization for the k-dimensional version. So Sherali-Adams is a well-known kind of relaxation or hierarchy of relaxations of an integer linear program. Okay, and what we get there is, yeah, the correspondence to the k-dimensional Weisfeiler-Leman algorithm. And then we have a number of similar characterizations which are not exact, but we have to shift the k up to constants factors. So for example, if we take the Lasserre instead of the Sherali-Adams hierarchy, it essentially stays the same, shifts the k a little bit. There's an exact characterization in a paper by David Robertson and my student Tim Seppelt, a very recent paper. If we look at polynomial calculus proofs of non-isomorphism, so basically that means that we use a Gröbner basis algorithm, but well, in such an algorithm we derive polynomials and we restrict the degree of these polynomials to k. then we basically also get a characterization of KWL. And then if we look at sums of square proofs of non-isomorphism, we also get such a characterization. So all these things are connected, but they show that this whole thing is fairly robust and there's many different ways to look at this. Okay, and finally, I want to mention a logical characterization. And that characterization that was known for a long time, since the early 1990s, is in terms of the K variable fragment of first order predicate logic with counting. Okay, and that's a logic that has been studied a lot in finite model theory, and the characterization is simply that KWL does not distinguish two graphs if and only if the graphs satisfy the same sentences of the logic with K+1 variables. So there's a shift of 1 in the K here. Okay, so that's pretty much the theory. No, I think I have one more section on theory, but now I wanted to go into another application, which I have worked on quite a bit recently and find fascinating as well, and that's to graph neural networks. So what are graph neural networks? They are deep learning architectures for graphs. And basically, what a graph neural network is a learned distributed message passing algorithm operating on the nodes of a graph. And it's actually not so hard to see that two graphs can be distinguished by a graph neural network if and only if they can be distinguished by color refinement. Okay, now that result has had quite some impact in machine learning on graphs, because now Weisfeiler-Leman is used as kind of a benchmark for expressivity of graph of different neural network architectures, so extensions of graph neural networks and so on. And in particular, this is nice because there's also a generalization to higher dimensional graph neural networks, which operate on tuples of vertices of a graph, and the higher dimensional Weisfeiler-Leman algorithm. And now people wrote many papers saying, so my version of graph neural networks with this additional operator is between 1 and 2 dimensional Weisfeiler-Leman, along these lines. Turns out the higher dimensional graph neural networks can also be useful in practice. So for example, we use them in a collaboration with chemical engineers at my university to build a model that tries to predict how well certain molecules may be suited for designing biofuels. That's what these guys in chemical engineering are working on. Okay, so it was easy to see that color refinement is not a complete isomorphism test. It's not so easy to see for higher dimensional Weisfeiler-Leman. So what's actually the power? Well, 2-dimensional Weisfeiler-Leman cannot distinguish non-isomorphic strongly regular graphs, such as these two. They are not isomorphic. 2-dimensional Weisfeiler-Leman cannot distinguish them. That's the smallest example of non-isomorphic graphs not distinguished by 2WL that I know. For 3WL, it's really hard to see, to find graphs that cannot be distinguished. Okay, and so that was open for a while. The algorithm was known till the higher dimensional version, well, the 2-dimensional till the 1960s, then the generalization to K-dimensional late 1970s. And people didn't know any examples of graphs not distinguishable by 3WL until Seifürer and Immermann proved that actually for every K we can find such graphs, and the size of these graphs is even linear in K. So if you turn this the other way around, to distinguish graphs of size n, you may need n-dimensional or omega of n-dimensional Weisfeiler-Leman. Okay, so this illustrates the construction here, but I'm not going into this. So now let's see what we can do. We have this result that shows us that as an isomorphism test, Weisfeiler-Leman is not complete, but it's still very powerful. And let me tell you a few results in that direction. Let's say KWL identifies a graph if it distinguishes the graph from all other graphs. Okay. And then we can say the WL dimension of a graph is the least K such that KWL identifies G. So it's at most N or N-1, but often it's much smaller. And something I proved is that for every class of graphs with excluded minors, there's a bounded K such that all, so a fixed K such that all graphs in the class have WL dimension at most K. Okay, so that means that on all these classes, for some K-dimensional Weisfeiler-Leman is a complete isomorphism test. For planar graphs, I think my original result for planar graphs gave a bound of around 14. Kiefer, Ponomarenko, and Schweitzer have improved this to 3. It's still open whether it's 2 or 3. Probably 2 is the correct answer for planar graphs. Okay, there's quite a few other results. For example, for interval graphs, the WL dimension is bounded. So there's also still active research here. But what this shows is that even though it's not a complete isomorphism test, the Weisfeiler-Leman is quite powerful and quite expressive. Okay, yeah, rank with K is also bounded. That's another result we have. Okay, and now the last thing I want to talk about is another generalization of Weisfeiler-Leman that we called deep Weisfeiler-Leman. And this has a very simple idea that I liked a lot and had a long time ago, and I always wanted to do something with it, but it turns out that to really implement this is nasty and quite complicated. But then eventually we did this. Let me just briefly tell you how this works. So remember what I said, K-dimensional Weisfeiler-Leman colors K tuple. And we can think of it in a different way. We create an auxiliary graph where the nodes are K tuples of the original graphs. And then we run the one-dimensional version on this auxiliary graph. Now, if we think about it, well, we create a node for all K tuples, but maybe we don't need them. I mean, it wastes a lot of space. And maybe the interesting part of a graph is just in a small region of the graph. So we don't necessarily need all K tuples, but it can be useful to generate longer tuples in certain areas of the graph. Okay, and we can do this much more space efficient. So basically, what we do is say we run color refinement, then we find, okay, there's some color class or maybe a few classes that look interesting. So we generate all pairs of vertices from these classes, add them to the graph. We have an auxiliary graph. We run color refinement again, okay? And then we may again see, okay, here's an interesting region. We do this again and again until we run out of space. I mean, we want to preserve space and say initially we say we want to use, say, cubic space. So we do it until we have generated too many tuples and then we stop. Question is, what can we do with this? Okay, so this is what I just described. Actually, we don't do this with color refinement, but with 2WL because it's more robust. And as I said, the technical stuff is quite nasty here, but we can do this. And then we can show that this algorithm basically has the same expressiveness as a logic also studied in finite model theory called choiceless polynomial time. And for example, we can show that choiceless polynomial time can distinguish those graphs by Weisfeiler and Immermann that they used to show that k-dimensional Weisfeiler-Leman is not a complete isomorphism test. So for all we know, it could be that deep WL actually is a complete isomorphism test or can be used to decide isomorphism. That's open, and actually it's related to some well-known open questions in finite model theory. Okay, let me stop here and just conclude with a few remarks. So we have the Weisfeiler-Leman algorithm, very simple algorithm, just a straightforward combinatorial algorithm. Probably one of the first things you think of when you think about how to decide isomorphism between graphs. But then it turns out to have many connections to completely unrelated ideas, homomorphisms, linear programs, logic. And it also has a range of applications that are maybe not expected. Isomorphism, okay, you would guess that it has. Linear programming or graph neural networks, maybe not. Okay, that's pretty much it. Thanks for your attention. Okay.